capture everything. So without further ado, Nick, whenever you're ready, go ahead.
Yeah, thank you very much. Can everyone hear me okay? I think we already did this, but I was going to say raise your hand if you can't hear me okay, but I guess that doesn't work. My name is Nick Hutzler. I'm from Caltech. And the three lectures that I'll be giving kind of generally discuss laser cooling and precision measurement in molecules, which you've heard different aspects about and will hear different aspects about from different people. So I'll hopefully talk about some non-overlapping aspects of that. Sorry, I can't be there in person. I had flights and everything, and Hossein kind of gave it away. You know, maybe there's some really exciting reason why I can't go, or maybe it's some mundane reason that you know, like I have children. If you'd like to see the slides, if you want to see a PDF of the slides, I put them here on my group website. I will also put them in some shared folder later, but if you just want to see them right now to follow along, here are the directions, how to find them. Just go to my group website, hutzlerlab.com, and then teaching ITAMP 2023, and you can find these slides there. You can let me know if you have any trouble getting them. And of course, please ask lots of questions. To the extent that I'm able to hear them, I will try to answer them. The first part, so part one is today, roughly. I want to talk about direct cooling of molecules, so expand a little bit upon some things you heard about and maybe talk about some things that you haven't. So in particular, I want to talk about buffer gas cooling and making beams out of buffer gas cooled molecules, but mainly laser cooling and trapping of molecules. So first, I'll start with buffer gas cooling, mainly in the context of being the kind of first step to doing laser cooling experiments with molecules. So you perhaps know, because you've heard earlier, why you want molecules to be cold. So I'm going to talk a little bit about how we make them, but also give just a kind of a brief review. So most if you want to make things in the gas phase, you can just a way to start is just to put something in like an oven and boil it, vaporize it. Most solids boil at over like 1,000 Kelvin or so, especially the types of things that I'll be talking about, which tend to contain metal containing molecules. And for atoms, that's fine. Electronic excitations are typically much higher energy than say the melting point. So you can throw a bunch of metal in an oven, you can boil it, you can make like a hot vapor, and they'll generally all be in the ground state, at least for especially the types of atoms people work with. So it's easy to access single internal quantum states, even at high temperature in a sense. So, you know, atomic spectra have these just very clean, distinct lines, whereas molecules don't at reasonably high temperatures. The vibrational degrees of freedom in terms of energy are roughly around 1,000 Kelvin, which is okay. That's fine. Maybe you'd populate a few or something. Rotation is a big problem. The rotational energy levels tend to be kind of 1 or a few Kelvin. So that means that if you just heated up some sample, even to like room temperature to get it in the gas phase, you'd spread your population out over tens or hundreds of thousands of states, maybe even more. So you don't get clear spectral features, you get just smears, again, at high temperature. So we want to cool to a few Kelvin first, for one of the reasons being that we want to be able to access single quantum states in the molecule. And it's an acute problem with many of the molecules that I will be discussing, because they're free radicals with low vapor pressure, meaning they're completely chemically reactive. They'll react with anything except noble gases. and they have very high temperatures to produce in the gas phase. And we'll see that at least for the types of molecules that we're interested in for laser cooling and precision measurement, those, it turns out, are basically requirements that they have these features. So what we do, and what a lot of other people do, one way you can cool these molecules, or is you can create them at a high temperature and then cool them to a low temperature using buffer gas cooling, so collisions with some inert gas. I will frequently use the acronym CBGB, cryogenic buffer gas beam. The basic idea is you have a cryogenic cell that you fill with helium gas or neon gas, some inert gas. You have a solid precursor. You vaporize that precursor, for example, with a high energy pulsed laser. So you produce molecules and a number of other things at high temperatures. But then they're cooled by colliding with these inert, non-reactive buffer gas atoms. And if this cell has a hole in it, you can just create a beam and shoot these molecules along with the atoms towards your experiment. The reason you may want to do that is because if you're trying to do, say, some highly coherent experiment where background gas collisions would interrupt that coherence, you have to sort of get rid of the helium buffer gas in some sense. And the easiest way to do that, it turns out, is just to expand the whole thing into vacuum and then grab your molecules some other way and then just pump the helium away using vacuum pumps. This technique works for just about anything. You can make atomic beams, you can make beams of like large biomolecules with like carbon rings and things in them. You can use the beam directly for spectroscopy or for precision measurements. For example, the ACME electron EDM experiment just uses a beam like this of thorium oxide molecules. You can also use this as the first step for laser cooling. So that's kind of the motivation for me discussing it a little bit. Some of the typical characteristics, there's, as I'll mention again later, there's a huge range of methods and techniques and technologies for these types of beams. So there are lots of ranges of properties in what I'll say. The temperature is just typically set by just the cryogenics that you have available to you. If you're using helium as your buffer gas, the beam is usually around 1.5 to 6 Kelvin or so. If you're using neon, it's around 16 to 20 Kelvin. A lower limit for this method is about 1 Kelvin, just because below about 1 Kelvin, even helium doesn't have enough vapor pressure to provide sufficient thermalization for the hot species that you introduce. Since you introduce these species at a high temperature, they have to have enough collisions before they leave the cell so that they're cold. And that means that the density has to be sufficiently high, and below around 1 Kelvin, nothing has any vapor pressure or appreciable vapor pressure. So these cells are usually installed inside. You can't really see the whole apparatus. Here's a picture from one of these cells at Harvard, installed in some big cryogenic refrigerator to cool it down to about 1.5 Kelvin. The velocity of the molecular beam, in this case, the beam is coming out here, and you can't see the aperture here, but it would be coming out this way, the molecule beam. The velocity is a little complicated. It's set by hydrodynamics of the gas cell. So the hydrodynamics of the flow of the buffer gas inside the cell, it turns out, are the kind of dominant determining factor in what the velocity of the molecules coming out is. It's typically around between 30 to 300 meters a second. There's a lot of tunability in terms of how you design these things. But there's usually a trade-off, which is that the velocity and yield roughly track each other. So meaning there are methods to produce a slower beam, which might be nice because you'd then have, for example, longer interrogation times for the beam. But typically those methods reduce the yield, like just the number of molecules that come out of the cell. Some typical numbers for these sources are you can get maybe 10 to the 9 to 10 to the 13 molecules per second out of these sources. It's very species dependent, as you may expect. I guess the lower limit on this is like 0. But these numbers are kind of, if you work hard and tried a few different things, you can usually get something like this. And if it's these numbers I'm quoting are for ablation loaded beams. So meaning you do something like this, you do a pulsed vaporization, because it turns out that for like laser coolable molecules and for CP violation, EDM sensitive molecules, that tends to be the best method. But that means you get a pulsed beam. You have a pulse production mechanism, you get a pulsed beam. These pulses are typically around a millisecond or so wide. And as far as the loading methods, how do you get the molecules in there in the first place? How do you create them or get them in there? There are a lot of different variations. With stable species, for example, you can flow them in. You can just have a sort of a gas line that goes into your cryogenic cell and flow them in. For unstable species, like these free radicals, for laser cooling and precision measurement, you have to produce them in the cell. You can't flow them down a gas line because they'll react with the walls of your gas line. So you produce them right in the cell. So then in that case, you're doing something like this. But something like this also has a lot of different variations. You can just directly ablate a solid precursor. So for example, thorium monoxide used in ACME just ablates a solid thorium dioxide precursor, which is chemically stable. You can also react ablation products with a gas that you flow in. For example, you can ablate calcium metal and then flow SF6, sulfur hexafluoride, into the gas, and the ablated calcium will react with the sulfur hexafluoride to make calcium fluoride. There are many variations on this approach. People have kind of tuned these gas cells, these buffer gas cells, to work to make like short pulses or very slow beams or highly collimated beams using stable gases or metals reacted with gases or sort of mixtures of powders. So there's a lot of wiggle room with this technique. But it can be used to make a lot of different species. The dynamics inside of these buffer gas beams and cells are surprisingly complicated. The main reason they're so complicated is because so in principle, the way it works is very simple. It's just you cool a hot gas by colliding with a cold gas, and that's, that really is how it works. However, if you wanted to say model this or quantitatively understand it, it's tricky, largely because the length scales, the relevant physical length scales, vary by something like 5 orders of magnitude across the beam. Inside the buffer gas cell, where there's a high density, the mean free path between collisions is usually less than 1 millimeter, but out in the beam after the gas is expanded and the density has gone down, it's usually over 1 meter. Also, these beams are very out of equilibrium, it turns out, largely because you have 2 species of mixed, usually very different masses. Like you have some heavy molecule and then a light gas, and the properties of those 2 things are usually out of equilibrium, meaning the buffer gas velocity and the molecule velocity, or the buffer gas temperature and molecule temperature, are actually usually not the same. And the properties of the beam depend very critically on, it turns out, just a few collisions which occur out of equilibrium. So for example, here is a simulation where the color coding shows a buffer gas flow pattern, in particular the sort of forward velocity in this direction of the buffer gas flow, and then these wiggly lines show particle tracing of heavy molecules going through this buffer gas flow. And it turns out that the properties of the molecules in the beam depend on just 1 or 2 collisions sort of right here. So nailing these properties down is very hard. and the reason that it's hard, the reason all of these things make it hard to simulate is because the beam properties, the molecule beam properties, depend very much both on the fluid-like flow of the buffer gas, but also the molecular flow of the molecules. And those have incompatible computational methods. So you can use fluid dynamics to model the buffer gas flow. You can use particle tracing to model the molecules, but you can't. You run into a lot of limitations if you use one method to try to calculate the other dynamics in certain limits. That's not always true, but at least in the limits where we operate these beams that we use for, say, like molecule laser cooling and precision measurement, it turns out that these methods really are largely incompatible with each other. Because of that, most CBGB knowledge is empirical, meaning people just kind of used intuition and experience and tried a few things to come up with a lot of these designs. Some of these designs were guided by modeling, but a lot of them were guided by like trying a bunch of stuff or intuition. But there have been a lot of successful approaches to modeling. For example, it turns out if you just use fluid dynamics and ignore the molecular properties, you actually get pretty good simulations. If you, for certain flow regimes, if you do sort of particle tracing, you can also get pretty good results. You can also do like a combination of both, like this figure here, where you do like a fluid dynamics calculation for the gas and then a particle tracing for the molecule. But at the end of the day, most of it's just trying things. So I've been talking a lot about ablation of these solid precursors. It being very common, especially for the types of molecules that I will talk about. And you may wonder, how do you choose what to ablate? There's a law. I made up this law while I was making the slides, but it's pretty true. It turns out the first law of making molecules from ablation is that if you ablate anything containing some atoms, you will get all possible small molecules containing those atoms. However, the yield will vary a lot. So you might get a lot, you might get not very many, you might get very stable production, you might get unstable production, and getting high production stably and consistently requires just a lot of, I don't know, trial and error and powder engineering and things like that. But if you're interested in experimental rules of thumb, metals and dense ceramics tend to be great. Soft, crumbly, chalky things tend to be bad. Realistically, just try a bunch of stuff, like go to some chemical website, search for the name of the thing you want, and just like buy all the chemicals that have that in it. Be careful doing that. You don't want to blow yourself up or something. But you'll find something that works usually. So, we just try a whole bunch of different things in the lab, like pellets and chunks and ceramics and, crystals and, whatever. So, here's a quiz. I haven't actually set up the poll. It's not actually a quiz. Which of these things, like, as I get increasingly desperate to make molecules in the lab, which of these things do you think I tried ablating? Or in, the group tried ablating, rocks from a museum gift shop, old watch parts, health supplements, dog antacid, or E, all of the above? The answer is, of course, E, all of the above. I have ablated all of these things in lab. And guess what? They all worked. They all made the thing that we wanted to make, although some worked better than others. Some worked surprisingly well. The dog antacid, it turned out, was like, we use that regularly in the lab. It's great. For the, not like we don't eat it. It's for, making molecules. Was there a question? Is it about dog antacid?
What kind of molecule?
I can now, yeah.
When you ablate, what molecules were you targeting?
Hold on. I'm going to put earphones in because I'm actually having a little trouble hearing you. So try again.
My question was that when you use this all of the above answer, what molecule were you targeting?
Oh, yeah. Every one of these was different. These were not all at once. That would have been very funny. But no, this was calcium fluoride. This was radium. This was water, actually. This was hydroxyl. So just different things for each case. So you can do, this works very well, but you can also, there are other kind of more sophisticated things that you can do. If you can't find any dog antacid. So one thing that we do, or, we meaning like the community, like people who do this stuff. One of the things you can do is you can, when you ablate this stuff, as you might imagine, you get lots of things. You don't just get the one molecule you want. You get all sorts of other byproducts and things. But you can, in certain cases, you can steer the molecule production towards what you want by optically driving reactions. So for example, something that we do in my lab is we ablate some empirically determined mixture of like terbium metal powder and terbium trihydroxide, which is some chemically stable thing you can buy. When we ablate that mixture, we get a bunch of terbium atoms and other things. If you drive the terbium to the excited metastable triplet state, that state reacts with other ablation products and makes YBOH, which is a molecule that we're interested in. And the reason this works is because this metastable excitation to this metastable state gives energy to overcome reaction barriers. So in the ground state, terbium and water don't react. And this is true of a lot of other kind of laser coolable or EDM sensitive molecules that I'll talk about have a similar structure and similar energetics. They can't react in the ground state, but if you excite the atom with a nice visible transition to this metastable state, then there is energy to overcome the reaction, and the reaction proceeds very quickly, and you end up getting your metal OH molecule. And typically you can get maybe 10 times or so more molecules just by shining in like an intense laser resonant with this atomic transition. It turns out that this all this energy, so there's several thousand Kelvin worth of energy left over after the reaction. Some of that goes into internal states of the molecule, many of which are cooled by the buffer gas. It also goes into like motion, you end up with like very fast moving molecules, but this is happening in a cryogenic buffer gas. So they're like instantly thermalized. And most of the internal degrees of freedom, like rotation, are also thermalized. It turns out that vibrationally, they're not thermalized. Vibrational quenching is very inefficient, meaning that it's hard to cool vibrational degrees of freedom with a buffer gas. It turns out that's useful for some of the things I'll talk about later. And this method has been done in buffer gases for a variety now of like alkaline earth atoms and a terbium, which is an honorary alkaline earth atom. And these molecules, the hydroxides of these molecules, will come back later because they are laser coolable. So, yes.
I wonder, like, when you say vibrational quenching is inefficient, one question is how do you quantitatively express that? And second is, do you have intuition why?
Yeah, so a way you could quantitatively express that is you could compare the elastic collision cross-section, sort of like the kind of momentum changing collision cross-section, which is what determines the thermal, like the motional thermalization. You could compare that cross-section to the inelastic cross-section of vibrational state change, or of like, say, rotational state change. And if you did that, you'd find that for example, the rotational state changing and elastic collision cross sections are usually about the same. They differ by like a factor of a few. But the vibrational cross sections, state changing cross sections are like 100 times smaller or something like that, maybe even more. And so this is something that you can calculate. People have also measured these. You can measure these cross sections by basically measuring like population changes in buffer gas cooled samples. But I think the intuition for why the vibrational state changing collisions are so inefficient is mainly, again, intuitively, that the vibrational period, the vibrational time scale is much faster than the like collision time scale. And so you just kind of average. So you just kind of average over the vibrational motion. The collision just kind of averages over the vibrational motion and is hard to change it. So it's kind of like it's a time scale mismatch. Since rotation is much slower time scales, the collision time and the rotation time are kind of more closely matched. But yeah, any other questions about that's all I was going to say about buffer gas cooling and molecule production before I switch over to laser cooling and slowing, unless there are any questions. All right. So a lot of the motivation for molecule laser cooling comes from things you heard about other times. Oh, yeah.
You were saying the rotational changing collisions, and I'm wondering, do we know like what's the complex lifetime of this collision or something like this?
Yeah, is John Bone there? Ask John Bone. He knows. Yeah, so I think for these, I don't know what the lifetime for the sort of like quasi-bound collision complexes for these things is.
This is John Bone from Jella speaking. My guess is it's short because it's buffer gas, it's noble gas, the potentials aren't very deep, density states are not high, but that's a given. Back to you.
Yeah, and realistically, so we've people have observed sort of like van der Waals complexes between, like very shallow actually bound states between like polar molecules and buffer gases, but they're so weakly bound that they tend to just be they tend to not survive in the buffer gas environment. So so they tend to just kind of be a small, they tend to not affect the dynamics or the populations or anything like that in a really appreciable way. Yeah, any other questions about buffer gas cooling stuff? Yeah, so laser cooling and slowing in molecules were motivated by the fact that lots of reasons. One of the reasons, at least that I'm motivated, is that precision measurements with molecules to say search for fundamental symmetries, beam experiments at least, are limited by time of flight. The beam only takes several milliseconds to fly through your apparatus, and you can extend that significantly by slowing and compressing the beam. Or even just trapping, then you can interrogate the molecules for a very long period of time. So for example, the Gila hafnium fluoride plus EDM experiment uses this to great success. They have long coherence times because the molecules are trapped and they can interrogate them for basically forever. There are also atomic measurements like with radium or ytterbium that use this to great advantage as well. For neutral species, this requires, at least for the types of experiments that I want to talk about with the types of species I want to talk about, requires ultra cold temperatures, meaning less than around a millikelvin or so. And that's because suitable conservative traps, again, for these types of molecules and these types of experiments are just shallow. They tend to only be about a millikelvin deep. You can make conservative traps out of static fields that are much deeper, but doing these particular types of experiments would be challenging. You could also imagine doing something like a fountain or something, or making a really long, super slow beam, and those all require some sort of further cooling beyond buffer gas cooling. One of the powerful methods we can use for these types of molecules is laser cooling. Of course, it's not the only way, but we like laser cooling, and we're excited about that because if you take some numbers that are kind of motivated by current state of the art, no one's done this experiment yet. People are working on it, but if you take some numbers that seem kind of realistic in the not too distant future, in terms of like quantum control and EDM sensitive molecules, for example, you could access CP violating physics at like the 1000 TeV scale, which is far beyond the reach of even conceivable particle accelerators. So that's fun. Let's see if we can try to make an experiment like this. So just a very brief review of the idea of laser cooling in case anyone here is not familiar with it. You can use lasers to apply forces to atoms and molecules. There are people in the audience who know much more about this stuff than I do. So you can ask them. You can use lasers to not just apply forces, but to cool and trap. And so this is it's a very commonly used technique in atomic and molecular physics. And the basic idea is to apply forces using typically nearly resonant lasers. So if you have some ground state and some excited state, you shoot a photon, a nearly resonant photon. The atom will absorb that photon and it will get a momentum kick. Momentum is always conserved. So it will say slow down a little bit as shown here. And then the atom or molecule will spontaneously emit this photon in not a random direction. I probably shouldn't say random direction, but in a direction with in a direction that averages out to zero. It could emit in some pattern, like a dipole pattern or something, but it will always emit into a pattern that has sort of average zero momentum kick. So after this one photon scatter, you have slowed the species by, on average, the linear momentum of a single photon, which is h over lambda. So you can extend this to cooling if you use, for example, if you have two counter-propagating lasers and you red detune them, meaning that they're slightly lower energy than resonance, because now if one of the atoms moves toward one of the lasers, say this laser, it will be Doppler shifted so that this laser is closer to resonance and it will feel a force pushing it that way. So you end up with a force that opposes the motion, opposes the velocity, which is a dissipative cooling force. It's a viscous force that gives rise to cooling. Ultimately, this method is limited by the fact that photon kicks are discrete to about a microkelvin or so. And you can go through and calculate, for this two-level system, you can calculate the dynamics and get things like force curves and find that you really do get over some finite range, at least, you get some dissipative cooling viscous damping force. And if you make, 6 pairs of intersecting lasers, you can make sort of a 3-dimensional cooling optical molasses. These lasers, as shown here, this setup here just gives you cooling. It doesn't give you any trapping. The species can still just kind of slowly diffuse out of this, intersection region here. Turns out if you add a magnetic field gradient and you are careful about controlling the polarization of the lasers, you can actually make a trap. So you can make cooling and trapping in 3D to make something called a magneto-optical trap, or MOT. And I'll come back to those later. So you thinking it as a two-level system, you apply these forces by absorbing and then spontaneously emitting. You typically need around 10 to the 5 cycles to say slow, cool, and trap a species. Those are numbers that I'll kind of motivate those later. There's a problem if you have some loss to some other channel that's not addressed by a laser. You stop scattering photons, there's no more forces. So just there's no more cooling, there's no more trapping, just everything stops. There's a simple solution. If you have a small number of lost channels, just add another laser. However, and this is very commonly done in atoms, but for molecules, because they have internal vibrational and rotational levels, among others, which are excited in spontaneous decay, it can rapidly become not feasible. And for some reasons I'll talk about, it's not just a matter of just buy more lasers. That's a part of the solution, but it turns out that if this problem is too bad, there's just nothing you can do about it. So let's figure out what to do. Brief recap of some relevant molecular structure. I'll talk about doublet sigma molecules. So those are molecules with a single unpaired s electron. Those have a ladder of vibrational states, which are typically kind of 10 terahertz or so. Each vibrational state has a ladder of rotational states, which are about 10 gigahertz or so for these types of molecules that I'll talk about. And then each rotational state is split into 2. So these features are fairly generic. Now from this part on, this is kind of getting specific to these types of molecules. Each rotational level is split into 2 states by the spin rotation interaction. So the fact that the molecular rotation is rotating charged nuclei creates a magnetic moment, interacts with the magnetic moment of the electron. So there's an interaction between S and N that causes a splitting into and couples the angular momenta into a quantum number called J. And then each of these is split further into another doublet due to the fact that at least if you have a nuclear spin of a half, which is the case for everything I'll talk about, so like fluorine or H has a nuclear spin a half that interacts with the nuclear spin of the electron because they both have a magnetic moment. So there's an interaction between the nuclear magnetic moment and the sort of coupled angular momentum, including the electron spin, which gives you the total good quantum number F. So for example, here's what the n equals 1, so single rotational quanta state looks like in a doublet sigma molecule like calcium fluoride or strontium hydroxide or something. And luckily, we can make our life a lot simpler by just ignoring these levels. The reason we can do that is because these levels are split in the kind of tens of megahertz range. And it's very, it's straightforward. It's easy to add frequency components to a laser in the kind of 10 to hundreds of megahertz range. So all of these states you can address sort of easily by just modulating your laser. Tens of gigahertz is hard. You could maybe bridge like 1 or 2 rotational levels with a modulator on a single laser. More than that just means you need to buy another laser. So for example, if you want to address the V equals 0 and 1 and 2 states, you need 3 lasers. You can't modulate a laser at 10 terahertz. So we've gotten rid of, so we've solved this problem, just modulate the laser. So now we'll look at, this problem. What do we do about this aspect of structure? So rotational branching. How do we keep the molecules from decaying into an unwanted rotational state? And we can use the fact that photons have momentum. They have angular momentum. They have like spin. They also have angular momentum in their radiation pattern. And a potential problem is that the molecule can start rotating upon photon emission. So this photon has momentum, angular momentum. It can impart angular momentum onto the molecule when it leaves by conservation of angular momentum. And that's true, that can really happen. But there's a trick, which you can use selection rules because angular momentum is always conserved. You can use that to your advantage. So if you say, look at a ground electronic state and an excited electronic state, rotational levels alternate in parity. So every time you add one rotational quantity, you switch parity. And so then there's a trick, which is you can drive an angular momentum 1 to angular momentum 0 type transition. Here, J is like generic rotational angular momentum, not necessarily this J from before. Turns out the notation is very inconsistent because you use different letters depending on the type of molecule. But these are just, these are the rotational levels. If you drive a 1 to 0 type transition, and then you look, where could it possibly decay to? There's only one place, which is right back down to where it started. You can't go from 0 to 0 because they have the same parity. You also can't go to 2 because they have the same parity. And then anything above 2, actually including 2, you can't decay to that. This is within the electric dipole approximation. So to within very good approximation, you can't decay to any of these other states because you would have to change the angular momentum by too much, by more than 1. You can only, in the electric dipole approximation, you can only change angular momentum by 1 using a single photon. So great, this works. This works very well. You can get sort of rotationally closed cycling by doing something like this. And these schemes generically exist. So this is a generic, rigid rotor spectrum that I drew. But if you look at like real actual molecules and real structure, you can find that for all the different types of electronic transitions that people have thought about or implemented laser cooling and trapping, you can always find transitions like this. Was that a question or an echo? Okay, it was an echo. Yeah, these schemes also exist even for like polyatomic molecules, which we'll talk a little bit more about later. They're more complicated though, because polyatomic molecules have additional rotational degrees of freedom. They don't just have one rotational axis, they have, more than one. A common feature of all of these is that they generally use transitions where the excited state has less angular momentum than the ground state, and that's that's to make use of this selection rule trick. So they all have they don't have more angular momentum in their excited state. They have at least the same or maybe less, and that poses a problem because whenever you have this situation, whenever you have an excited state that doesn't have more angular momentum than the ground state, there will always be dark states, which cannot scatter some polarization. So for example, the simplest example of this is that if you look at, say, the stretched states, so the states with maximal M in the ground state, from the plus M state, you can't drive a sigma plus transition. Because there is no state up here with M equals 2, because this state does not have more angular momentum. Same with sigma minus. So that means this state is dark to at least this polarization of light. And this is a problem because magneto-optical trapping, as I briefly alluded to earlier, relies on your ability to scatter the correct photon polarization. So it turns out that MOTS work by using a magnetic field to selectively choose whether you scatter like a sigma plus or a sigma minus photon to always push you to the middle. So if you have states, if you have internal states that can't scatter a particular polarization, then they'll be kind of dark to the MOT force. And that's not good. There are a lot of ways to deal with this problem. There's, you can check, I recommend if you're interested, you can see this review or some other great reviews about molecule laser cooling. But one way, which I'll briefly mention, is you can rapidly alternate the polarization just to prevent accumulation in the dark states. So if you rapidly alternate the polarization of your beams between sigma plus and sigma minus faster than the rate at which they accumulate in these dark states, then you'll always scatter photons. Rapidly switching a laser polarization, it turns out, is technically straightforward. You can just buy a thing from Thor Labs that does that using electro-optics, even pretty quickly, like megahertz. A trickier part is you must also alternate the magnetic field synchronously. So you can't just alternate your sigma plus, sigma minus polarizations. You have to alternate the magnetic field in sync with it, so at like megahertz. But a common solution these days is to use in vacuum resonant magnetic coils. So here, these are sort of inch scale magnetic coils with some resonant LC circuit so that you can drive a current in here at a few megahertz and make what's called, an RF mott. So in summary, rotational branching in molecules is non-trivial, but it's a solvable problem. There's sort of always something you can do to deal with it. A trickier problem is vibrational structure. Vibration doesn't have any selection rules. There's no angular momentum. Well, sometimes there's angular momentum associated with vibration, as we'll talk about later, but at least in diatomics, vibration has no angular momentum. There's no selection rules. So in principle, any state can decay to any other state. And so a way that you can think about it is your ground electronic state and your excited electronic state have some potential energy surface, which is the sort of energy given some fixed distance between the, say, two nuclei. And vibrational states are basically eigenstates of this potential. You find this potential, you find the eigenstates, those are the vibrational states in the molecule. And within the Born-Oppenheimer approximation, that the electron motion is much faster than the nuclear motion, the electronic transitions you treat as basically instantaneous relative to the vibrational motion, meaning that if you're in this, a wave function that looks like this right before the decay, right after the decay, you're still in this vibrational wave function, except now this is no longer an eigenstate. Now these are the eigenstates. So you'll reproject this state onto all of these different states, meaning that you have some probability of decaying from, say, this state to any of these states, vibrational states down here, with a factor given by the wave function overlap squared. And these are called the Frank-Condon factors. And so since this potential energy surface is determined by the chemical bond, in some sense, you need to find molecules where the valence electrons don't participate in the chemical bond, so that when you excite or de-excite the electron, the bond basically doesn't change. It's actually more complicated, and I'll say a little bit more about that later, but this intuitive picture, it turns out, is pretty good. So here's an example of a molecule that does not work very well. Calcium oxide. Calcium has 2 valence electrons, oxygen wants 2. All the electrons in the molecule are involved in the bond. So when you excite one of the electrons, the bond changes a lot. So you don't get potential energies. You kick the potential energy surface a lot, and you can have the molecule start vibrating. Calcium fluoride works great. You end up with 1 non-bonding electron, which is kind of centered on the calcium. It doesn't participate in the bond. So whether this excited or ground, whether you're in the excited or ground state, the potential energy surface is basically the same. And by the way, this doesn't have to be F, it could be like OH or something. And I'll say more about that later. So here are some, this is sort of a cartoon sketch. These are some, actual potentials and calculations and stuff. Here's an example. Lithium hydride is bad. It's of this type where all the electrons are involved in the bond. So the ground state and the excited state potentials look really different. The wave functions look really different. And so if you're, say, in this state here, when you reproject on this very different looking basis from this very different looking potential, you spread your population over, a dozen different states. Calcium fluoride, as we saw, is diagonal. The ground and excited state potentials are very similar. The wave functions basically look kind of orthonormal. So 0 overlaps with B0 very well, and it doesn't overlap very well with anything else. And so if you look at the probability of changing the vibrational state upon electronic decay, on a log scale, it goes down pretty quickly. So With just one laser and one repump, you can, you have over 99% by closure of vibrational leakage. And so that's basically what you do is you find a molecule that looks like this, that has this type of structure, and you add a few repump lasers. So these are, lasers that address these leakage channels. And it works. You require one laser per vibrational repump, again, because these wavelengths differ by something, given by the vibrational energy, which is big enough you can't modulate it with one laser. So you have to buy several lasers. Each of these lasers, you then have to put sidebands on to address the hyperfine structure. So for example, this is strontium fluoride. This was the first laser cooled molecule. So you get one laser per vibrational level and vibrational repumps. And then each of these lasers you modulate with sidebands to address the spin rotation and fluorine hyperfine structure, which again is not that hard to do with modulators. And then doing this, you can scatter, enough photons to cool into a magneto-optical trap, or even, transfer into a dipole trap, and all sorts of other things that you'd like to do with molecules for precision measurement or quantum information studies. So there have been now 4 different species that have been loaded into a there are others that have been laser cooled but not yet trapped. 4 different species have been laser cooled and trapped. Strontium fluoride was the first one, and actually in not fewer than 10 years ago. So this is all pretty recent stuff, and it's moving very rapidly. But it's still very hard. And I'll discuss some of the kind of remaining contemporary challenges. So to say a little bit more quantitatively, what electronic structure do you look for? So you're looking for, non-bonding electrons. But can you look a little more kind of quantitative, or can we understand it a little more quantitatively? The answer is yes. Generally, you get laser coolable structure when you have a metal-centered s electron rising from an alkaline earth or type atom with 2 valence s electrons that makes a single bond to a fluorine. So you end up with a metal-centered doublet sigma state, so single valence electron with sort of no orbital angular momentum. And it turns out that it's even better than that, because it's not just metal-centered. This s electron isn't just metal-centered. It turns out it's actually kind of polarized away from the bond. The bond itself, the electromagnetic fields of the bond mix in some excited p-type orbitals and push the electron away from the bond. So it's actually kind of decoupled from the bonding region. And if you do like a proper quantum chemical calculation of like what are the orbitals and wave functions for these types of molecules, you see this is the case. Like the wave functions, the electronic wave functions have this like dimple around the bonding region. So they really avoid the bonding region. And that's what gives you this good decoupling of electronic and vibrational degrees of freedom. And just to reconnect with the initial motivation, that's good news for CPV searches, because these S and P-like electrons are good for symmetry violation searches like EDM searches or nuclear symmetry violation. Those all rely on having a large degree of penetration into the nuclear core by the electrons, and these types of orbitals have that. So that's great. And so that means you can find a number of heavy EDM sensitive laser cool molecules, many of which are being actively pursued, mostly fluorides for diatomics. A lot of different fluorides for both nuclear and electron symmetry violation searches. So there's a very strong comparison to be made between these types of molecules and just like alkali atoms, which is, you have, and even if you look at the orbitals, you can see there's a lot of similarities. You go from say in an alkali atom, you go from like a doublet S to a doublet P state for laser cooling. Here you go from a doublet sigma to a doublet pi. So, you know, overall, there's this reduction of symmetry due to this bond being here, but they have a lot of similarities. It's a single valence electron. It's a strong optical excitation. You know, it's a few EVs, so kind of, you know, visible 10 nanosecond radiative decay lifetime or so. These are often compared to like the alkali atoms of molecules. If you want to actually do like a laser cooling experiment, so you start with CBGB. You don't have to, but that's what people use these days because you can get high fluxes of these kind of weird reactive free radical molecules. You can cool them internally to concentrate population in a few internal states. So that's great. But there's a catch, which is that the beam has a forward velocity. It's not, it has a finite temperature, so it has a finite velocity distribution, but it's also moving in the lab frame between, say, 30 and 100 meters a second, or in terms of energy, you know, it's typically kind of tens of Kelvin or so worth of energy. And that's typically above the capture velocity of a MOT. So the idea of a capture velocity is that a MOT is both a trap and dissipates energy, but it has a finite size and it can dissipate, and it has a finite energy dissipation rate. So it can't stop and trap arbitrarily fast species. It can only trap up to some finite velocity, which is called the capture velocity. So for example, you know, here's a simulation for atoms showing, you know, if you send them in with some spread of velocities, below some velocity, they'll get cooled and trapped and stuck in the trap at, you know, zero-ish velocity at, you know, the trap center. But if it's too fast, like it'll get slowed, but it will still escape the MOT region before being stopped. So for atoms, this is usually kind of, you know, 50, you know, tens or something of meters a second. But for molecules, it's typically smaller, much smaller. You like under 10 or under meters per second. So even these very slow beams are still not slow enough. And one of the reasons that capture velocities for MOTS are so slow is because there's a large number of effective ground states, and that reduces the photon scattering rate. If you look at, for example, like in an atom, you can find what are called type 1 transitions. That's the case when you have more angular momentum in the excited state than in the ground state. One consequence of that is that you don't have any dark states. You can kind of always scatter any polarization. But it also means that your scattering rate effectively goes up. If you look at a type 2 transition, where the excited state does not have more angular momentum than the ground state, which is exactly the kind that you have to use for a molecule, you basically have a bunch of transitions that you can't drive. So it overall reduces the scattering rate. Another way to think about it is there's competition from stimulated emission, right? So if I drive, say, if I excite up to here, these two lasers all have a tendency to stimulate emission back down. So in the fully saturated limit, you know, for those of you who, you know, think about the dynamics of atoms and molecules and lasers a lot, in the fully saturated limit, the population is distributed among all these states. So here it spends 3/4 of the time in the ground state. Here it spends 3/4 of the time in the excited state. And so the scattering rate, since only the excited state can decay, correspondingly, the scattering rate in this situation is lower. So you need to start with your already slow beam, and then slow it a little further. And it turns out experimentally, this is basically the hardest part, is taking these beams and slowing them to within the capture velocity of a MOT. Once they're basically slowed to within the capture velocity of a MOT, they usually proceed without too much trouble. But making these beams consistently slow is very hard. And And also, but there are experimental methods to do that. And that's where I'll pick up there next time, since it's now half past. So are there any questions about anything?
Oh, thank you, Nick. Yeah, so are there questions?
I wanted to ask about the slide on the compatibility with the CPV searches. I guess I missed the point. I guess that maybe Dave Demelsky also mentioned a little bit about the sensitivity due to this probing of the nuclear, but like, what do you mean here that these molecules are compatible with that?
Yeah, I mean that for basically all CP violation searches, whether it's like electron EDM or like nuclear EDMs or something, the sensitivity, meaning the amplification of the effect by the internal molecular fields, is always proportional to the wave function overlap of the electron on the nucleus. And when I say these are compatible, what I mean is that these have a lot of, just by their nature, they have a lot of S character and a lot of P character. And S and P are the types of wave functions that have the most overlap with the nucleus. As compared to like if it was like a delta state or a phi state or something, then these lobes would be pushed further and further out from the nucleus. So that's what I mean by they're compatible, meaning they tend to have like high sensitivity to CP violation while still having this laser coolable structure. And there are counterexamples either way. So for example, like thorium oxide is very sensitive to CP violation, has really good wave function overlap, but it does not have this laser coolable structure. There are also laser coolable atoms and molecules that have this electronic structure that are also not very sensitive to CP violation because they're light. So the wave the sensitivity to CP violation is determined by the electron wave function overlap at the nucleus and by the mass of the nucleus. So you want both of those things to be large. And so that's why you basically are interested in like heavy fluorides that have this kind of sigma type electronic structure, meaning they have a lot of S-like characters. So they have a lot of wave function overlap with the nucleus, and then they have a lot of charge in the nucleus from being heavy.
Right, but maybe another question is, what is the downside of these molecules versus, like the triplet delta or the beryllium oxide?
Yeah, and I'll say a little bit more about that tomorrow, but the short version is those can't be laser cooled. So triplet, there are no, and for fairly good reasons. It's not just, it turns out that kind of if you make a big table and check them all, it doesn't exist. There are kind of good reasons why you don't expect triplet delta molecules to be laser coolable. And it's because they basically don't have this structure. There is one exception. It turns out there's a light titanium oxide has a triplet delta structure and is laser coolable, but it's very light. So it's kind of more like an exception.
And my question is the other way around. It's more like these seem to be very nice. So what's the downside of these molecules? Like some of them are not.
Yeah. So downsides. I guess there's there's two, I suppose. Although both of these for these molecules that I've listed, there are kind of two downsides. One is that because they're rigid rotors, the nearest opposite parity states are rotational states. So you need very large electric fields to polarize these, as opposed to like a triplet delta molecule, you need basically nothing. These molecules, you need big fields. And another downside is, at least for these, this isn't true for this, for thallium fluoride, but for these, for the electron EDM molecules, they have an unpaired electron, which is, I mean, it's this unpaired electron. But it means that they're magnetically sensitive. Whereas these triplet delta molecules, there's this kind of cancellation and they're very, very insensitive to B fields. These molecules are totally sensitive to B fields. However, there are some tricks you can play, which I'll talk about next time, that address both of those. And the short answer is, like, if you use polyatomics, you can specifically address both of those concerns. And then the downside is that polyatomic molecules are complicated, but so is thorium oxide.
I have a question. So when you were saying, like, it's better to find a molecule with unpaired electrons so that when you go to the excited state, the potential energy surface don't change the center of mass that much. So I wonder if this rule actually applies to all of the molecules. For example, one molecule that comes to my mind, one type of molecule comes to my mind is alkali plus alkaline earth. Like, is this kind of molecule? I think they probably can exist. Do you think it's possible that for them the fundamental factor is also pretty diagonal?
Yeah, alkaline earth. So alkali plus alkaline earth.
Yes.
Dave DeMille would really know the answer to that. I think those molecules. Take what I'm saying with a grain of salt, because it might not be correct. But my understanding is that those tend to not have very good, or I think they don't have very good Frank-Condon factors because they tend to be very covalent. There's an exception with silver, as you may hear later. But they tend to be very covalent, and I think the ground states of those are actually almost like van der Waals complexes instead of being like deeply bound molecules. And so I think the bonds are just kind of very like floppy. But that being said, you could probably look up what the Frank-Condon factors for these things are. But my suspicion is that they're probably not very good, just because these at least in these types of molecules, people have studied systematically the effect of like how ionic the bond is. And it turns out that to matter, there's a reason that like laser coolable molecules tend to be like diatomics, tend to be like hydrides and fluorides and stuff, just because they make very ionic bonds. You really pull that electron away from the one atom and kind of bind it like deeply in the bond, so it's just kind of like gone. And if something is more covalent, that tends to not happen, and it tends to be harder to like isolate the electrons from the valence electrons from the bond.
That makes sense. Yes. Thank you.
Other questions? Not, then join me in thanking Nick. Thanks very much. We'll see you tomorrow then. All right.
See you
Take care.
tomorrow.
Thank you. Bye.